All right, this is part one of HVAC 121, which is a lecture, your first one out of this book. So let's go to page 370, all right? Page 370 in your book. And it says safety checklist: when troubleshooting electrical malfunctions, disconnect the power, lock and tag the panel. When checking continuity of resistance, turn off the power and disconnect the leads. Ensure the meter probes come in contact with only the intended terminals. Make certain that all electrical connections are tight. Make certain that unused wires are properly capped to prevent them from coming in contact with other conductors. All right, so the first thing it says is introduction. It's a good place to start, you know. Each control must be evaluated to its function, major or minor. Recognizing the control and its purpose requires its understanding its use in the system. Studying the purpose of a control before you take action will save a great deal of troubleshooting. So look for pressure lines going to give pressure controls and temperature activated for temperature controls and determine what it is. So then the next paragraph gives you some terms you should know. Electrical devices either power consuming or non-power consuming. So what is power consuming device? A power consuming device uses power. It consumes it and uses it. It's called a load. All right, if you're taking notes and you want to write what's in your book right there, that's in your book. It uses loads, okay? It's called loads. It uses power. Some examples are a resistance coil, like a strip heater, or a magnetic coil, like you would have a solenoid coil, a coil and a contactor relay. The next term your book gives you is non-power consuming. And non-power consuming, they're called switches. Switches pass power, okay? Oh, one of the students knocked my, oh, never mind, there's nobody here. Well, you gotta blame somebody. These are passing power, called switches. They pass power. All right, they pass power to what? The load, the power consuming load which uses the power. Loads and switches are wired in series with one another. If you go back to your notes on Monday, 2 weeks ago, you'll see that we wrote down the wiring diagrams for switches and loads in series and in parallel and how they work, and we did the math. Okay, that goes along with that. Multiple loads, of course, are wired in parallel. Multiple loads are wired in parallel, and that's what we did on that Monday. Multiple switches are wired in series to the load. And of course, if you have a power supply and a path, current will flow. Now, next in your book, it says, the concept of the load and switches can easily be clarified using a simple light bulb circuit, and that's what I drew, and that's what we're going to talk about. The object is to wire the light bulb to both sides, hot and neutral, to have power. That's in picture 15.1 in your book. Notice this: for any power consuming device to consume power, it must have potential across it. Potential voltage is the voltage indicated on a voltmeter between two power legs. So hot and neutral could be 24 volts. Hot and neutral could be 115 volts. Okay? If it was two-phase, you would have 120 and 120, so your potential voltage should be 240. Now, we talked about this the last couple of weeks, so I think you pretty much understand that, so I'm not going to keep discussing the same exact thing with you over and over and over. All right, so let's get you a little closer now to this board right here so we can discuss this. Now, this is the way it's drawn in your book, just the way it's drawn in your book, and that's the way I want to talk about it, okay? This is what your book shows on page 371 at the top. it says switches pass power. Here is a light. The light is the load. The power passing device is the switch. Passes power to the power consuming. Switch in series to the load. So you have to have hot and neutral connected to the load. You don't have hot and neutral connected to the switch. If you did that, it'd go boom, boom. Okay? So we don't do that. Now your book also says fuses pass power until they burn. So here I do a second one, and this is the next picture in your book. And it says the fuse passes power until it gets overheated and it pops and breaks the circuit. And right here, we have a thermostat set to pass power to the light bulb. So what's happening here? If we had a meter and we put 1 meter lead, can you see that? 1 meter lead right here, and the other one on solder hot, we get 115 volts. Notice the switch is closed. So if I took this one and this one, I'd read 115 because it's a continuous path. If I went to the next along that path, remember, as long as you got a path, current will flow. Here's my power supply, my path, here's 115. Across the fuse, 115. Continue down the path, 115. However, notice what happened. The load, the switch right here is open. The thermostat's open. So the load is not getting the continuous path of potential power, potential voltage. So right here to this side of the thermostat, I read 0 volts. 0 volts. And that's the way that's read when you're in the field. One quick way to check things, like I teach on the trainer board with the light bulbs in the lab, is to do the hopscotch. Oh wait, power stops here, that must be open. Okay? This is exactly written in your book. You actually have this in your lab manual, and you're going to do this in the lab too with your lab manual. All right, so that's how you hopscotch across there. Okay? Now your book says, let's do some troubleshooting now. Let's do a little troubleshooting and see what we can find. Remember, whenever there is a path in power supply, it will flow. So let's go ahead and fool with this a little bit. Let's go ahead and close this switch and send power to the light bulb. Now I'm reading 115. Because you got to remember, it's necessary for you to remember that the power now is continuing the path. Now we have this. Light comes on. We got a continuous path to the load. All the switches that are wired in series are closed. So we have a closed circuit of power. Now, what if I took, your book says, what if you took your meter and put it to the load? So let's go ahead and erase this. Okay, we're recording now. Okay, so let's go ahead and erase this. Now, if I put my meter here, what am I going to read? 115. I'm on this side of the circuit, whether I have this side of the meter here or here, I'm reading 115 volts. I could take that meter lead and put it here, 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 here. As long as they're all closed, I will read 115 volts. But notice when we open it, we stop the path, we get 0 voltage to our light, and it turns out. That's the purpose of a light switch in your home. You do use that little toggle switch up and down, it kills the power. All right, shuts it off. Now, what if I did this? Let's go ahead and close this. Take this meter lead here and this meter lead and put them like this. That is 115 volts. I should have power to my light. That's 115 volts. All right, any questions about that? Now let's say my circuit broke open. Notice it breaks the path. Now, what do you think I'll have? The path is broken. I got the potential voltage coming to the light, but it doesn't continue the path. So you're correct. Right now, we have 0 volts. But what if I put my meter back over here? Now, 115 volts again. So that's the part of your book right there called troubleshooting. So remember this, your book says, if there's voltage at the light bulb and it does not burn, it's defective. Now when I go over there and hit that light switch, right, like this, and it gets dark, now I'll walk in the room and I turn on the light switch and the light doesn't come on, do I automatically think something's wrong with the switch? No, you're gonna think, hey, there's something wrong with the light bulb. So that brings us to the next principle. If I have power to my light and my light does not burn, the light bulb is bad. So the principle said, you could say anytime I have power to my load and my load does not work, the load is bad. Because you have power to it. If you have power to it, then it should work. But let's say it's not working. Guess what? Light bulb bad. Power at the load, load's not working, it's bad. Any questions about what you just learned so far? All right, so that covers the whole part of your book right there. Next part, which will be your second lecture, part 2, we're going to get a little more in depth with something called troubleshooting a complex circuit. Okay?